Welcome to ECE 165. This is a lecture when we're going to discuss how to build memories like SRAM, DRAM, and so on. So let's go ahead and get started. So this is a new topic on memories. And if you're following along at home in the textbook, of course I do recommend, reading chapter 12. That's in Weston Harris. Okay, so it turns out there are many types of memories available to us. There are things called random access memories. And these are what you typically associate with memories in computing systems. These are things like SRAM, that turns out to stand for static random access memory. There's things like DRAM, which stands for dynamic random access memory. And now that we know things, know those words very well, static and dynamic, it turns out that they're actually relatively easy to understand with our knowledge of static CMOS and dynamic CMOS. Now these are what we would classify as volatile memories. And what that means is that if the power supply of our system goes away, so does the content of the memory. Okay, that's in contrast to a ROM, which the word ROM means read-only memory. That doesn't necessarily imply non-volatile, although usually it does, but it's not necessarily true. This was what we would classify as a non-volatile memory, and I just realized I spelled that wrong. Okay, so what we mean by non-volatile is that if the power supply of the system that we're using goes away for whatever reason, then we won't lose our data. It turns out that other memories like flash memories and so on are also non-volatile memories, which is why they're very popular for things like USB keys and so on. Then there's other type of memories that can be accessed differently. There's serial access memories. So random access memories implies that we can access any individual unit within this memory at any time. We don't have to go through a special procedure where we access other units before we do that. That's in contrast to a serial access memory, for example, like a shift register, a FIFO, first in, first out queue, etc. There's many different types here. So in these, we serial access the memory. So for example, in a shift register or FIFO, we shift in data into the memory, and the first data that's shifted in will eventually be shifted out. But we can't just access, memory bit 13 directly in our FIFO or shift register memory. We have to go through and read all of the bits that were shifted in before that bit in order to access it. Okay. Then there's another interesting class of memories called content addressable memories, or CAMs. Okay, these are really interesting. Normally in a memory system, what we do is we insert an address. That address corresponds to some location within the memory, and we pull the data that's stored at that address. In a content addressable memory, what we're doing is the opposite. We're providing the content, and then the memory is supposed to figure out what address it's located at. So you can imagine there's some interesting opportunities to use CAMs for search, for things like routers and so on. They use CAMs extensively. So we're not going to talk about CAMs any more than that, just brief mention. What we're going to focus most of our attention on is on random access memories today. So as it turns out, random access memories, or I suppose memories more generally, but usually random access memories, are typically laid out in arrays. Okay, so let's go ahead and draw a picture of what we mean by that. Okay, so let's imagine that we have, you know, some large array. Actually, you know what? I'm going to move that over just a few notches here. Some large array, maybe looks something like this. Okay, within that array, we have a memory unit, one unit cell. Okay, so this is a, let me draw an arrow here. This is a single cell which stores 1 bit of information. Now, it turns out that there are ways to build memories where each cell stores more than 1 bit, but in general, the case is that we tend to have one cell store 1 bit. Okay, so if we want to, and then we have an array of a bunch of these all over this array here. Okay, so if we want to access this bit, we need to be able to read out from it. Okay, and we read out typically through a row column architecture where we activate a row within the memory and activate a column and then read out that 1 bit. Okay, so we call this column the bit line. This is the column that's going to actually read out the stored data. And this is called the word line. Okay, it's called the word line because we can activate a whole line at once. This will activate a readout process, and we can activate multiple bits at once, so perhaps we can read out a whole word, a digital word, right? Okay, so in order to access this each row in the memory, we typically have what we call a row decoder. Okay, so this is a row decoder. And the reason we have this is there is a lot of potentially large number of rows in this memory. Okay, we don't want to have to route all of these wires all the way to the the microprocessor core. That's just a lot of wires. So what we tend to do is have a decoder where we have a smaller bit width of information that comes in here. Okay, so I'll fill in this bit information shortly, but it turns out we also have a column decoder as well, which largely does the same thing. These are our column circuits, and we'll talk about what goes into these column circuits shortly, but let's just assume that there's a whole bunch of columns in here. You know, this is a very big memory array. Okay, so what we'd like to do from the microprocessor's perspective is we want to provide an n-bit address. Okay, and this n-bit address is going to be broken up into n minus k and k bits that will access the row decoder and the column decoder. Okay, so let's just write a few of these things down. So if we have an n-bit address, we have 2 to the n bits in our memory that are split into a n minus k by k matrix of memory cells. Okay, so that's the overall structure of this. So the decoders, what they do is they take an X bit input and select one of 2 to the X outputs. Okay, so at a very simplified case, if we were to somehow merge the row and the column decoders, or let's say the column circuits was k was equal to 1 or 0, I suppose as an example, then we would have an n-bit address. There are 2 to the n possible memory cells in there, And so we have to choose one of those 2 to the n memory cells. So we take our n-bit digital word, we insert it into our decoder, and that will activate one of those 2 to the n lines at the output of the decoder. Okay, and so in that example, we were only looking at the row, but in practice, this happens for the row and for the column. So that's for a decoder. We also have things called the column circuits. So what the heck are these? So interestingly, the column circuits are used for read and write, and I suppose I should complete the drawing here. Then we have data coming in or possibly going out, depending if we're reading or writing into the memory. So the column circuits either drives data onto a bit line, this is for a write operation, or it will sense the result on a bit line using typically what we call a sense amplifier. The reason we need amplification will hopefully be clear shortly. Okay, so that would be for a read operation. So let's go ahead and dive into one example of a memory cell and make sure we understand what all of the circuits for this overall structure will look like. So the first cell we're going to look at will be an SRAM cell. This is the most popular memory for on-die microprocessors. So it turns out a memory cell for SRAM is something very familiar to us that we've basically studied already. Now we'll input it into kind of SRAM format. So the best way to understand this is to look at the SRAM cell from both a writing operation perspective and from a reading operation perspective. Let's look at it from a writing operation perspective first. Okay, so it turns out the SRAM cell, a typical SRAM cell, is nothing more than a circuit we've already seen. It's a back-to-back converter. Okay, that is the basics of an SRAM cell. Now, we need to be able to write and read from this SRAM cell, and to do that, we employ what we call access transistors. Okay, these access transistors are activated through the word line. Okay, now this connects to, all over the chip, and we'll say this is, or all over the array, this is the word line. Okay, so what this means is that the access transistors are connected to the word line. All right. So when we assert the word line, when we send it from logic 0 to logic 1, actually let me give myself just a little bit more space here, logic 0 to logic 1. When we assert the word line, what we're doing is we are turning on these access transistors. Okay, so that is allowing us to see inside what's happening within this cell here. All right. Now, obviously, these access transistors, they're not just floating. They have to connect somewhere. And as it turns out, they will typically connect to what we call the bit line. Okay. So this is what we call the bit line. And you'll note that there's also another one over here. So if that's called the bit line on the left, then this must be called bit line bar. I guess there's no hyphen there. Okay, so it's basically, as it turns out, a differential type of measurement. So these bit lines go up and down. They're connected all over the place. There's many of these cells in place. in this larger array, and so on. Okay. So how do we do a write operation? Well, let's say we want to, and this is part of our example, we want to write a logic 1 into this memory cell. And let's say just for the moment that it was storing a 0 on this side and a 1 on this side. Okay, so we want to write a logic 1. So what we do is we set the bit line to logic 1 and the bit line bar to logic 0. Okay, and then we assert the word line. So we change it from 0 to 1. When we assert the word line, what we're doing is we're turning on these access transistors. So there's a conflict here, right? On one side, let's look at the left access transistor. On one side, on the left side of the access transistor, we have logic 1. On the other side, we have logic 0. This logic 0 is being kind of stored statically by this back-to-back inverter structure. So what we're trying to do when we're writing is we want to push a very strong logic 1 onto the bit line, strong enough that it overwrites the content of the memory. So this changes to a logic 1, and the exact opposite thing happens on the other side. It changes to a logic 0. Once we are done writing this new value to the SRAM, then we deassert the word line, set it back to 0, and now the SRAM is now storing this new value. Okay, so this is how we write data to an SRAM cell. Now this is the most basic SRAM cell. There are many other types of SRAM cells, although this is by far the most popular. We call this a 6T SRAM cell because it's composed of 6 transistors. 4 transistors that comprise the 2 inverters plus the 2 NMOS access transistors. Now you might be thinking, why are we only using NMOS transistors for those access transistors? Why don't we use a transmission gate? And your thought process is correct from the point of view of performance. If we care about being able to drive strong ones and zeros, then yes, a transmission gate would be much better than just a single NMOS pass transistor. However, memories are typically not necessarily optimized for performance. They're typically instead optimized for density. What we want to do is cram as many bits as possible into the smallest amount of area. So when you buy a computer, you of course prefer a computer with 16 gigabytes of RAM instead of 8 gigabytes of RAM, right? So this is the reason why we prefer memories that are more dense. So if we added that those 2 PMOS transistors, this would become an 8T cell, and the density of memory would go down actually rather significantly. So for this reason, we tend to want to sacrifice performance a little bit in the pursuit of achieving higher density. So that's how we do a write operation. Let's now look at how we do a reading operation. And I'm going to struggle a little bit to fit this on one slide, so please bear with me here. Okay, so we have at the very top of our bit lines, we have some pre-charged transistors, just like we have in dynamic logic, actually, even though this is a static logic circuit. Okay, and then we have our bit cells, and in this bit cell, I'm actually going to draw it more deliberately than I did last time. What I'd specifically want to do here is I want to draw the actual transistor level implementation of those inverters. Okay, so this is let's call it the top inverter as an example. And then we have a mirrored version of that inverter on the other side. This would perhaps be the bottom inverter, if you will. Okay, so what we do here is we connect the output of one inverter. Actually, let me just draw this access transistor first. So we connect the output of one inverter to the input of the other inverter, and likewise over here. Okay, so this is a diagram of this back-to-back inverter structure. So this is our entire SRAM cell here. And I've compressed things a little bit more vertically than I would have liked ideally here, but hopefully this will still work out. Okay, so it turns out we have a word line that comes into the circuit, goes all the way through the circuit, and we connect our access transistors to this word line. Now on the other side, sorry, let's complete the bit line drawing here. Okay. So over here, actually, let me give myself just a little bit more room. We also have a bit line on the other side, bit line bar. And the entire bit line is pre-charged to a specific value, in this case, VDD. This pre-charge is activated by a clock called phi2 bar. Okay, so let me make a little annotation here. And in the pursuit of saving space, I made things a little bit too compressed, but I think it'll work out. Okay, so this is what we call the bit line conditioning circuits. Okay, there's one per column. Okay, so the purpose of the bit line conditioning circuits is to pre-charge the bit line, we'll call it bit line, to logic 1. Okay, we'll try and understand why momentarily this is a good idea. Okay, so this is our first memory element in the array. There are more 6T cells below it. And eventually, we have to read the data out. Okay, and so what we end up doing is, and there's, more of these guys here. What we end up doing is going through what we called earlier a sense amplifier. Okay, so this is the bit line. This is bit line bar. Okay, and this over here, I should say, is the word line on top of here. Okay, so this is what we call the sense amplifier, or SA. So we still don't quite know why we need this yet. So let's go through an example. In this example, let's imagine that this cell is storing 1, and this cell, or the complementary side of the cell, is storing a logic 0. So let's go ahead and look at what would happen with phi2. Okay, so let's imagine phi2 does a pre-charge phase here, and then a 0 the rest of our timing cycle. Okay, so when phi2 is 0, phi2 bar is 1, and so those PMOS transistors are not activated. And let's just say that the word line doesn't turn on until somewhere over here. Okay, so the word line is off, phi2 is off, and so those PMOS transistors are not charging up. So frankly, we don't know what bit or bit bar are equal to before that point in time. Okay, we don't know what they are, so let's just draw them as either 1 or 0, and we're just not sure. Okay, so as soon as phi2 activates, then we know that both bit and bit bar get pre-charged to logic 1. Okay, simply through the action of those bit line conditioning circuits. They pre-charge everything to logic 1. Now, after phi2 disengages, we have a little bit of space between that and when the word line engages. Okay, between this space, the word lines are basically just held where they are, just like they are in dynamic logic. Okay, so you might be thinking, hold on, you said that this is a static RAM. Why are we using dynamic logic techniques? And that's true, this is a static RAM, but what that's referring to is that we are statically holding the data with this cross-coupled inverter structure, but we rely on dynamic logic in order to read the data out. Okay, so it's dynamic storage, not dynamic readout. It's static storage with dynamic readout. Okay, so far, hopefully everybody's on the same page. Now, what happens when the word line activates? When the word line activates, we engage those access NMOS transistors, and we have a little bit of conundrum here, right? On the right-hand side, we have a logic 1, which is the same as the pre-charge value of the bit line. So nothing is going to change for the bit line. But on the bit line bar, we have a logic 0 being stored. Meanwhile, we had pre-charged the bit line bar to logic 1. So there's a conflict here, right? And it turns out that the SRAM cell is going to win. Even though these SRAM transistors are tiny, they're super small, the smallest possible transistors that you can design, simply because we prefer to design for density in an SRAM rather than performance. These are the smallest transistors you can possibly lay out. But that one NMOS transistor in the right inverter that's tying its output to logic 0 is statically on, whereas the word line is just dynamically floating there. Okay, so even though it's a small transistor and there happens to be a lot of capacitance on the bit line, it will slowly charge down. Okay, and then eventually it'll, just level out after the word line stops. Okay, so after a certain period of time, we're going to have a differential voltage derived or achieved between bit and bit bar. So let's write down a few observations here. Okay, since there are many parallel cells in a column, bit line capacitance can be large. Okay, so what I mean by that is we tend to put lots of cells in each column, right? That's the advantage of an array system, right? So we have lots of cells in each column. Each of those cells is connecting to the bit line. So if we have n cells in a column, then we have n times c worth of capacitance on the bit line. As I mentioned earlier, we also want minimum size inverters within our SRAM cell for high SRAM density. Okay, and in fact, most process design kits allow you to break the design rules just a little bit in order to make SRAM cells even more dense than they otherwise could be possible. But they're very regular structures, and so the first circuits that people tend to build in new process technologies tends to be SRAMs, just to kind of push the process limits a little bit. So, but because of this difficulty, we have lots of capacitance on the bit line and we have tiny little inverters in our SRAM cells, we say thus bit line discharging rates can be very slow. Okay, and that's really the big problem that we have with SRAMs, and this is the reason, in fact, why we use what we call sense amplifiers. And we'll get into the exact details of those sense amplifiers momentarily. So even though those bit lines are, discharging rather slowly, there are ways to do what we call large signal sensing. And this would be the basic way that we would all immediately understand on how to do the sensing here. Okay, so let's just draw a smaller section of this circuit. Okay, so we have our pre-charged transistor activated on phi 2 bar. Okay, and this will be connected to an SRAM cell through an access transistor that's activated by the word line. And within this SRAM cell, we have our cross-coupled inverter structure as follows. Okay, so I'm just drawing basically half of the SRAM cell. Then we go through our entire bit line, and then eventually we get our output. Okay, so in this particular case, this would be looking at bit bar in the example that I showed earlier. Okay, so bit bar does discharge, and eventually it'll discharge all the way to 0. If the leakages and so on work themselves out. So we could just put an inverter here as kind of our sensing element. Okay, that would work fine. Well, it would work. It functionally works, but it's not super fast. Okay, so one way to improve the speed here is to use a high skew inverter. Okay, so for large signal sensing, we tend to use a high skew inverter. So the question would be, why? Okay, well, the reason is because the output only falls, right? Just like domino logic, right? So we pre-charge the output. It's pre-charged to VDD, and either one side of the bit line stays at VDD or it discharges, and vice versa. Okay, because the output only falls, high skew inverters are more sensitive to falling edges. Okay, and so as a result, they are going to detect this falling edge a little faster and speed up the operation of our circuit. So this is a good thing. So the previous approach that we just discussed is called large signal sensing. So presumably, there's going to be the opposite called small signal sensing. And the general thought process here is that the large signal sensing approach, it functionally works okay. However, it's really slow still, even with the high skew inverter. Okay, so we say sometimes large signal sensing takes too long. We're impatient people. We want high performance out of our computers. So we need to do something different. Okay, so the idea is let's amplify. I'm going to move that over just a little bit. So let's amplify bit minus bit bar to sense faster. Right, this is technically a differential, or I suppose a pseudo-differential signal. And so couldn't we just amplify this? And as soon as we see a small differential change between bit and bit bar, we can amplify that result up to VDD and then make a quick decision that we don't have to wait for it to discharge all the way down to 0. So that's definitely possible. We could just use a normal differential amplifier, like one that you've studied for use in 102 or 164 or something like this. That'll work perfectly fine. However, we are digital designers here, and so perhaps there's a better thing we could do that consumes less power, right? A differential amplifier requires a static bias current that will consume static power. We don't like static power in our digital circuits, so let's think about something different that we could do. Okay, so it turns out this is where this concept of a sense amplifier comes in. Okay, and again, I'm going to be a little vertically compressed for space here, although I'll try and do a little bit better job this time. Okay, so let's imagine we have our pre-charged circuits up here. This is connected to Phi2 bar. And let's imagine that we have our first SRAM cell in here. It's a connection of back-to-back inverters. Okay. So they're connected as follows. And this is connected to the word line and the word line. Okay. And then we have a whole, column of these guys. And we want to amplify the difference between bit and bit bar, and we want to do so very efficiently. Okay, so the basic idea here is let's build the beginnings of a differential amplifier. Okay, so we'll use a differential pair. And yes, I know that this is a digital design class, but as part of digital design, we do have to have a little bit of knowledge of analog design. Digital circuits, anyways, are made up of analog parts. So we have some sort of tail current source, although in this case, we're not going to bias this tail current source with a current source, or we're not going to bias it as a current source. We're going to do something a little different. So we'll get into what that transistor actually does in a moment. But for now, I want to finish the rest of this design. So normally what we do here is we will then have either a resistive load or a load based out of transistors that effectively act as resistors in our differential amplifier. In this case, I want to do something a little different. In fact, I'm going to load this circuit with a cross-coupled inverter pair. Okay, so I'm going to basically put an active circuit in my load. All right, this is a very strange idea, at least at first. So we have our inverter here as follows. Okay. And I'm going to draw this slightly differently than I did for the other case there, for the SRAM cell. Okay, so these are cross-couple inverters. The output of one is connected to the input of the other one. Okay, so we call this circuit that I'm going to box in red here a sense amplifier. And specifically, this is referred to as the StrongARM sense amplifier. Okay, it was basically invented by ARM, the artisan, and so on, and that's why it's referred to this. Okay, so how this works is it works like a differential pair but with regenerative or positive feedback. Okay, so what we're doing here is we are intentionally leveraging positive feedback to latch in data quickly. Now specifically what we do is we have an extra signal down here called the sense clock, CLK. Okay, so we want to latch the data in quickly on the rising edge of sense clock. Okay, so how does the circuit work? All right, so what we do is when sense clock is 0, there's no way for static current to flow through the cell, and so basically what we end up doing is we end up, and I'm not showing these transistors here, we end up pre-charging the internal nodes to VDD of the StrongARM sense amplifier. And then once the bit lines start to discharge, we start to develop a slight potential difference between bit and bit bar. Okay, so we develop a small potential difference between bit and bit bar. And then after a certain amount of time, when we expect to have developed a large enough difference between bit and bit bar, then we turn on sense clock. Okay, and what this does is starts to cause current to flow through the differential amplifier, or the differential pair rather. So if current flows, say for example, more in the left side where bit is being activated because it's staying at logic 1, whereas bit bar is being discharged, and so there's a little less current flowing through the right NMOS differential transistor, then what's going to happen is there's more current that's going to flow into the left inverter as opposed to the right inverter. As a result, the left inverter is going to be able to create its correct output value faster than the right inverter. And the outputs are differentially measured here, by the way. And so as a result, it can, and then the positive feedback between these two back-to-back inverters here kind of really adds some extra gain into this amplifier and creates a very quick decision. Okay, so this is the main reason why we use something called the StrongARM sense amplifier, is because it allows us to make very quick decisions. Okay, now there's a few other advantages here. There is no static power consumption. Okay, and the reason for that is, most of the time sense clock has not been activated, but even when it is activated, once the inverters, the cross-coupled inverters latch out to a static logic value, these are inverters, right? And so there's no static current that's flowing through in inverters. All right, so even when sense clock is activated, once the decision has been made, there's no more static power going on here. So this is a major advantage over what we'd have with a normal differential amplifier, as an example. Now, I'll say another point here, that this is a very important building block in many other circuits, used also in analog to digital converters and other circuits, but basically used as a comparator. Okay. So I have one final question before we move on to the next topic. So we spent all this time talking about SRAM, but we have to do this weird small signal sensing and so on. So my question is, why use SRAM at all? We studied flip-flops. Why not use flip-flops instead? We studied flip-flops, and although they were perhaps a little confusing at first, now that we understand them a little bit better, they're actually pretty easy to understand. They work fine. We don't have to have these weird, small signal sensing. We don't have to have row and column decoders and so on. We've added a lot of complexity to our memory elements here. Flip-flops store memory perfectly well. In fact, using the same mechanisms as SRAMs do. So why don't we just use flip-flops? All right, so maybe pause your video for just a moment. Think about this. It's important that we understand the reason for this. Okay, so I'll let you do that now. So the answer, and it's a very simple answer and one that we've actually alluded to already before, is density. Okay, flip-flops are not super dense. You need lots of transistors to store 1 bit of information in a flip-flop. An SRAM only requires 6. Now, of course, there's overhead from the column and the row circuits and the sense amplifiers and so on, but if you build a large enough array, those get amortized out effectively. All right. So I would argue that, and everybody would argue, that the reason we use SRAM instead of flip-flops for large data storage reasons is for density purposes. Okay. Now, on that note, let's go ahead and talk about the next topic, and that is dynamic RAM, or DRAM. Okay, so as the name implies, DRAM stores information dynamically as the name implies, of course, on parasitic capacitance, C parasitic, sometimes called or C cell, the cell capacitance. Now, because of this, as a result, DRAMs must be periodically refreshed. So we have dynamic storage, and so as a result, we have to periodically refresh our DRAMs. Okay, and that's, you know, a downside of their approach. So it turns out that DRAMs are extremely simple conceptually to implement. All right. In fact, we can build a DRAM with 1 transistor. So we'll call it a 1T DRAM cell. And perhaps you already have in your mind what this 1T DRAM cell might look like. Okay, so the basic idea here is we have the same overall array structure. We have our word line. We have a bit line. And we connect the bit line to a transistor whose gate is connected to the word line. And on this side of the transistor, we have some amount of capacitance. We'll call it C cell. Okay, that's the whole DRAM memory cell. Okay, so let's try and understand this. Let's go through an example of how we would do a write operation into a DRAM cell. Turns out it's pretty easy. So we have our word line. We have our bit line. In this case, we're going to drive the bit line to be equal to 1. Bit equals 1. Okay. So what we do in this case is we assert the word line. We have it go from, I guess not equals, we have it go from 0 to 1. That turns on this transistor. And what it does is it charges voltage onto this capacitor. So this charges from 0 to 1. And then once we've stored that value on the capacitor there, we deassert the word line, and the voltage that's stored on here is now logic 1. Okay, now there is a little caveat there in that it's not actually a logic 1, because as we know, NMOS transistors do not pass a strong logic 1. If we ignore subthreshold conduction, this will charge all the way to VDD minus VT. And if we want to do this operation quickly, that's basically all it'll get to. So we have to take a loose definition of what we mean by logic 1, but it turns out that this turns out to work okay for DRAM design. So let's go ahead now and look at a read operation. Okay, so a read operation will be somewhat similar to a SRAM read, but of course a little bit different. So we have our word line. we have our bit line, and we're going to load the bit line with some sort of amplifier whose specifications will be discussed shortly. We have our transistor here and our capacitor here. Okay, so it turns out that we do reading operation in 3 steps. Okay, step 1 is we pre-charge the bit line to VDD over 2. Okay, so step 1, and I'm not showing the pre-charged transistor, but we'll charge it to VDD over 2. Step 2 is we enable the transistor. There's only one transistor here, so that hopefully should be fairly straightforward. So step 2 is we convert the word line from 0 to 1. And step 3 is we sense the voltage change on the bit line. Okay, so let's go and try and understand what's happening here. So this voltage here was approximately VDD. We've pre-charged the bit line to VDD over 2, and then we turned the transistor on. Okay, that bit line is pre-charged, and then it's just floating there. Likewise, the capacitance on this side is also just floating there. So effectively what we're going to have is some charge sharing, right? Whatever capacitance is on the bit line is going to share with whatever capacitance or whatever charge is stored in the cell. And so this is going to go to approximately VDD over 2 plus some delta V. Okay, and this is step 3. All right, let's try and understand what this delta V looks like. Okay, so let's imagine we have a voltage range between ground and VDD. And initially, we pre-charged our device to VDD, or our bit line rather, to VDD over 2. So this was step 1. Okay. Now in step 2, we are going to activate the word line, and which turns on the transistor. Okay, so if the transistor happened to be storing a logic 1, then this voltage is going to start to go up because it's sharing charge with the word line and the cell capacitance here. Okay, so let me just add some annotations here. So we say that we have some bit line capacitance here, and this is C cell in there. Okay, so we're going to start to share charge because the cell capacitor was charged to VDD and the bit line was charged to VDD over 2. When we short these two capacitors through this access transistor, then the charge is going to go up a little bit. So this is step 2 when the voltage starts to go up, and then at step 3 we make a decision. Okay, the amount that this goes up by is called delta V. Okay, and delta V in this case is equal to VDD over 2 times C cell over C cell plus C bit. It's easy to derive this. Q equals CV. Charge must be conserved during this process, and so you can easily kind of derive what goes on here. Okay, but I'd like to make a few remarks here. So the bit line capacitance can be large for large columns, right? If we have a large column, bit line capacitance can be very large. On the other hand, the cell capacitance is usually very small. In the name of density, we don't want to put a huge capacitor there for every bit line or for every cell. We want it to be extremely small. So therefore, delta V, delta V is very small. This is why we need an amplifier. Okay, so I did mention that this curve happens if we happen to be storing a logic 1, but the opposite curve will happen if we happen to be storing a logic 0. Okay, but the delta V is roughly the same. All right, so the astute viewer here may notice a problem. Okay, it's actually a big problem. Oops. Perhaps think about this before I proceed, actually. See if you can figure out what this big problem is. So I'll give you a moment to pause the video and think about it. Okay, so you've thought about it. Maybe you've come up with the answer. Maybe you have no clue. Let's talk about it. A DRAM read, remember, we're just trying to read the contents of the cell. A DRAM read is destructive. Right? We were storing a nice logic 1 or a nice logic 0, and now at the end of the read cycle, we're storing VDD over 2 plus delta V, where delta V is small. So we're basically storing the worst possible logic value, or the worst possible voltage to represent a logic value, VDD over 2. Okay, so that means every time we read, we destroy the contents of the memory. Okay, so let's just elaborate. So the previously stored value is erased during a read. Okay, so that's a bummer. You know, what's the solution to this? Well, the solution is fairly easy. It's a little annoying, but I guess, you know, it's the best we got. Is we follow every read with a write. So every time we read something from a DRAM, we must then write into this DRAM. Okay, so yeah, it's kind of annoying. So you might be questioning, why the heck are we even using these? So after all is said and done, why the heck do we use DRAM anyways? You know, we have to, the values don't stay there for long. They have to be refreshed. We have to rewrite after read. You know, there's all these difficulties. Why bother? So let's just write that down. Why DRAM? Why do we use DRAM? Well, let's write down those negatives first. It must be refreshed periodically because it's a dynamic circuit. It's holding charge on a parasitic capacitor. We must do a rewrite after every read. So every time we read something from the DRAM, we have to then write back to the DRAM. That takes time and energy. It turns out they typically require a special process for generating a high value of C cell. If we were just to use the parasitic capacitance of the transistor, C cell is tiny. Compared to C bit, the bit line capacitance, it's so small that the generated delta V is just too small to reliably sense. And we do want to have the sensing be extremely reliable. And so what they typically do is they have a process in some CMOS technologies called a deep trench capacitor. And effectively what it is if you look at your gate of your MOSFET, and maybe it looks something like this. It's implemented in CMOS. We have a doped region here, N+. What they typically do is they have this extra large doped area here, where they put a dielectric in the middle here, which basically allows them to create a very large capacitor. Now looking down from the top, this is occupying the same area as our normal CMOS transistor, but because we're leveraging the vertical dimension here, we can potentially create a very large high density per unit area capacitor. But this does require special process steps. These are tend to be more expensive. And in addition, because of some of these constraints, we tend to have higher latency when we're using a DRAM cell. Okay, so again, the question is, why the heck would we use DRAM? There's all of these downsides. Well, there's one enormously big upside, and that is density. Okay, we only need one transistor plus perhaps our deep trench capacitor in order to build our DRAM cell, and that's hugely valuable. Okay, so when you build a computer, on the microprocessor itself, you tend to have caches, L1, L2, L3 caches, and so on. These tend to be implemented with SRAM. SRAM is compatible with normal process technologies. You don't need special steps or anything like this. It's not as dense as DRAM, but then again, you don't need the caches to be quite as large as you do for your nominal RAM. So when you quote the RAM of a computer, it's usually not talking about SRAM. If your computer has 8 gigabytes of RAM, of memory, this is usually talking about DRAM that is located on chips away from the microprocessor. Okay, this is why you can upgrade the memory of your computers, depending on if you can actually access them or if they're soldered directly to the PCB. So, and the reason that that's the case is our memory, or our RAM, implemented with DRAM simply for density reasons, right? It's better to have 8 gigs of memory than 4 gigabytes, and likewise, it's better to have 16 gigabytes of memory rather than 8 gigabytes of memory, right? And so density is the name of the game there. That's why we use DRAM. So I want to spend just a little bit of time looking at one of the circuits we discussed, but didn't go into any detail on, and that is the address decoder. So how do we build an address decoder? Well, it turns out the most basic way to do this is actually rather simple. Okay, so let's imagine that we have a 3-bit example. We have bit A2, A1, and A0. So there's 3 bits here. All right. So what we do is we take A2, and we also generate an inverted version of A2. Take A1, and we create an inverted version of A1. We take A0, and of course an inverted version of A0. And then what we do is we tap off these lines in order to generate and pass them into an AND gate in order to do the selection. So let's say we're trying to select address 000. Okay, so what we'll do is we'll take the output of A0 bar with A1 bar and A2 bar and the results together, and that is activating word line 0. Okay, so if we have A1, A2, A0 equal to 000, then we're trying to access that row in the memory. And so by ANDing these results together, we'll activate word line 0. Likewise, if we want to decode 001, we would just take A0 and then A1 bar and A2 bar. Okay, and this will activate word line 1. And so on and so forth until we get to the final value. That would be word line 7. Where we take A2, A1, and A0 and AND the results together. So that's word line 7 in this 3-bit example. So what this does is it requires 2 to the n AND gates, each with n inputs. So as you can imagine, as we scale up the size of these address decoders, they can get extremely big and messy. Okay, so we do have to keep that in mind when we're designing these things. So I'd like to go through a nice example that kind of ties a lot of different things that we've learned in this course together. What I'd like to do is basically design the sizing for an SRAM cell and for the row decoder. So specifically, the example is compute the optimal delay of a 2 to the n word by 2 to the m bit SRAM, right? Capital N is equal to 2 to the n plus m. Actually, you know what? I'm not going to use that terminology. I'm just going to say total number of cells is equal to 2 to the n plus m. Okay, so first of all, let's draw what we mean by this circuit. So we have our addresses. Okay, I'm not going to draw all of the n lines going through here, but they're going to connect to, some AND gates. These AND gates are then going to drive a word line. These word lines are also going to be next to bit lines, which are going to attach to access transistors that are connected to inverters. Now, for the purpose of this logical effort calculation, which is what we're going to do, I don't need to show the PMOS transistors because the PMOS transistors are just there to hold the bit lines high, and there's no action there. We only care about discharging the bit line. Okay, so I'm only going to show the NMOS transistors in the pull-down network in this case. Now, for this particular model, we're going to assume that the transistors are all of size 1. They're all minimum size transistors. I'm also going to assume that just the wiring of the word line is going to have 1C of capacitance associated with it. And then we'll have the other side of the SRAM cell here, access transistor connected here. And then this connects to the bit line on this side, and that keeps going. Okay. These are also of size 1 over here. Now this is for the cell that we are activating. There will also be cells that we are not activating, right? And a cell that we're not activating is going to have the access transistors attached, but the circuits, the NMOS and the PMOS and so on, are not participating in any pull down or pull up activities here. So we say these are of size 1, this is 1C, and so on. Okay, so this is our rough diagram of our circuit. Now remember, there's 2 to the m bits per word, and this has to be an n input AND gate. Now, if you'll recall, for an AND gate, G is equal to n plus 2 over 3, and P is equal to n. Okay, so before we can kind of compute these results, let's summarize a few, or rather, before we can compute an optimal, let's just take a step back and think, how the heck are we going to even do this? All right. Well, when we talk about computing an optimal delay, the first thing that should come to mind is logical effort, right? So this allows us to look at the delay of multi-stage logic in order to come up with some, optimization approach here. So this is indeed a multi-stage logic network. We have an address, that's our input signal. It goes through an AND gate. The AND gate then activates an SRAM cell, which turns on and one side of the SRAM cell is going to discharge the bit line. Okay, so how do we go ahead and optimize this? Well, we need to generate, H, B, F, G, etc. We need to do a little bit of alphabet soup in logical effort. But before we do that, let's just summarize a few things about this circuit. So first of all, we can say that there are, let me give myself a little bit more room here. There's 3 C per word line cell. Okay, what I mean by that is for any word line that connects to a cell, there's 2 C of capacitance by connecting to those access transistors, and an additional 1 C of capacitance just from the wiring itself. Okay. The logical effort of an SRAM cell is equal to 2 for SRAM cell. Since the current capabilities is half of a regular inverter, right? It's half of a regular inverter because we have 2 NMOS transistors of size 1 connected in series, right? So it's as if we've built a NAND gate and sized the NMOS transistors of size 1 instead of size 2. Now, of course, the reason we do this is for density reasons, it's not optimal from a logical effort perspective, but it is for density reasons. In addition, we have 2R of cell resistance, right? We have 2 NMOS transistors in series. They're both of size 1, and so therefore their total resistance in series is equal to 2. Okay, the next thing we want to look at is and I'm going to take a little bit more room and go to the side here, the bit line diffusion capacitance. Okay, so in other words, any bit line that connects to a cell will see only a single NMOS transistor of size 1. So it's going to be 1 C per cell. What this means is that there's 2 to the n C per bit line, right? Because there's 2 to the n access transistors that are connected to each bit line. So from this, we can compute the parasitic delay of the SRAM cell. That's going to be equal to 2R times 2 to the n C, okay, which is equal to 2 to the n plus 1 RC. Okay, so in other words, we can say that P, the parasitic delay, which is just equal to tau over 3RC, where 3RC is tau I and V, is equal to 2 to the n plus 1 over 3. Okay, so now we have little p for the SRAM cell. So what we can do now, and I'm going to revert back to black now, is we can compute a few other things. We can compute G. Okay, what's the logical effort of the AND gate? It's n plus 2 over 3 times the logical effort of the SRAM cell is 2. All right. Now the only thing we don't really truly have is the electrical effort. Okay, so we're going to just take a guess here. Okay, so we're going to set the electrical effort to be equal to 1/2. This is a guess. It depends what we're loading the circuit with and so on, but it turns out it's an educated guess. It's something reasonable to think about. Okay, we can compute the branching effort. This is equal to 2 to the n plus m. And the reason is because the address line goes into n AND gates. And then feeds m cells on the word line. Okay, so that should hopefully make sense. So now we have G, H, and B. That means we can now calculate F, which is just equal to G, B, H, which is equal to 2 to the n plus m times 2 over 3 times n plus 2 times 1/2. Okay. Likewise, P is equal to n, that's the parasitic delay of the n input AND gate, plus 1/3 times 2 to the n plus 1. Okay. Then we say often F hat is optimal at around 4, right? We said the stage effort is often optimal to be approximately 4. So what we'd like to do is set the number of stages by breaking apart the AND gate. If we need a larger number of stages than is drawn here, or by buffers insertion, if we want to use very large fan-in gates, to be equal to log base 4 of F. Okay, so therefore, the delay through the circuit, capital D, is just 4 times log base 4 of F plus P, which is equal to 2 times M plus N plus 4 log 4 of N plus 2 over 3 plus N plus 2 to the N plus 1 over 3. Okay, so that's the answer. Let's do a numerical example for a 32 by 32 bit SRAM. It turns out that, n equals 5, that's for 32, and we can do the calculation, and it turns out that D is equal to 146 RC. Okay, so again, this is an interesting example where we take a little bit about what we learned in logical effort. We take what we learned today about SRAMs and decoders and used it to make a design that had pretty good or near optimal sizing, at least according to the assumptions that we've made here. Now, I do recognize that this was a lot to take in one example. It turns out that I did intentionally select this example because it is also discussed in the book. So I do encourage you to read section 12.2.7.2 for more details, because they go through exactly the same arguments that I just went through when they are computing their answer. So again, if you're confused about this at all, I do highly recommend that you go through that example in the textbook to make sure everything is as clear as possible.